Hello again, it's Lucas Fow. I am back again today to go over the thermodynamic topics in Chapter 5, namely being the Clausius inequality, parts of the Kelvin-Planck statement, and kind of an overview of what thermal reservoirs are. The Clausius statement of the second law of thermodynamics basically puts into words what most would probably consider common sense, being that with two bodies, heat cannot be transferred from the cooler body to the warmer body. Heat will only travel from the warmer body to the cooler body. The easiest way that I can think of demonstrating that Clausius statement I had talked about earlier was with these two cans of soda. The one on the left, the Dr. Pepper, has not been in the refrigerator, but the Diet Pepsi has, hence its temperature is lower, and barring any external effects, heat is moving from the warmer Dr. Pepper can to the body of the Diet Pepsi can, which is cooler, and it cannot go the other way, barring any other external effects on these two bodies. Before discussing the Kelvin-Planck statement, it's kind of important to go over the term thermal reservoir. A thermal reservoir is any system that, regardless of heat input or heat output, its temperature isn't going to change. The most commonly applicable thermal reservoir I can think of is the Earth's atmosphere, as anything on any scale, or pretty much any scale that we would be looking at, the amount of heat coming out of the atmosphere, going into the atmosphere, is negligible in determining what temperature the atmosphere is going to be at and stay at. Another example could be the Earth's ocean, or a mixture in which both of the phases coexist because the temperature isn't going to change. Now, knowing about thermal reservoirs, we can delve into what the Kelvin-Planck statement actually says. And what it says is that any thermodynamic cycle that is only interacting with a single thermal reservoir, the work has to be either negative or zero on the thermodynamic cycle, aka work can be done on a thermodynamic cycle by one thermal reservoir. No work can be done, but work cannot be done on the surroundings if the cycle is only interacting with a single thermal reservoir. But if we look over at two or more thermal reservoirs, that breaks down and we are able to have positive work done with a power cycle. To demonstrate this, assuming that the warm cup of coffee is a thermal reservoir and the jar of coffee is a system undergoing a power cycle, we can conclude that the can of coffee or power cycle is unable to do work on the thermal reservoir, but the thermal reservoir is able to do work on the can of coffee. Now, assuming that the power cycle or a can of coffee is sitting between the cooler thermal reservoir of the can of Pepsi and the warmer thermal reservoir of the can of coffee, it is possible that no work is being done by the power cycle. It is possible that work is being done on the power cycle, and it is also possible now that the power cycle is producing positive work. It is doing work on its surroundings.